To run a modern artificial intelligence locally, the industry standard usually demands a machine with a dedicated graphics card and dozens of gigabytes of RAM. This is not that machine. This is a 2017 Surface Book 2, powered by a dual-core Intel i5 processor and a strict maximum of 8 gigabytes of DDR3 memory. This look at the system's task manager reveals a razor-thin margin for error. If an AI model requires even slightly more RAM than this physical 8 gigabyte ceiling, the operating system is forced to swap active data onto the internal SSD. This paging slows text generation to a crawl, or causes the system to fail entirely. Memory is only the first obstacle. This graph shows the CPU utilization during an active generation. An older dual-core processor is immediately overwhelmed by standard workloads, hitting 100% capacity almost instantly. This creates a dual bottleneck. First, a memory bottleneck, where the physical neural network is too large for the RAM.
Second, a compute bottleneck, where the processor cannot calculate the necessary math fast enough to be useful. Running AI on this hardware isn't a matter of brute force. It requires specific technical choices to reduce the model's footprint and maximize the efficiency of the processor. The arithmetic of an 8 gigabyte budget is unforgiving. A standard installation of Windows 11 often consumes up to 5 gigabytes of RAM just idling, leaving very little room for anything else. First, a lightweight operating system, like Windows 11 LTSC, shrinks the idle footprint to 1.5 gigabytes. Still, standard uncompressed AI models require tens of gigabytes. We solve this with quantization, compressing the model's weights into tiny 4-bit integers to fit perfectly within our 8 gigabyte limit. This makes it possible to run small language models with fewer than 3 billion parameters. Models like Gemma 3.4b for general chat or Microsoft's Phi 4 Mini for logic can operate within a footprint as small as 2.5 gigabytes. By combining a minimalist operating system with compressed model architectures, the memory bottleneck is successfully managed. But fitting the model into memory is only half the battle. If the dual-core CPU is simply too slow to calculate the trillions of math operations required, the AI remains unusable. Standard CPUs process one number at a time. AI requires SIMD, single instruction, multiple data, handled by AVX2, which packs multiple numbers into a single register. The llama.cpp engine detects AVX2, allowing the CPU to crunch massive parallel batches of compressed data every clock cycle. Text generation is one thing, but image generation is a much heavier lift. It requires calculating more than 260,000 pixels simultaneously rather than predicting one word at a time. Rendering images requires a strict workflow. Close the text model to free memory, keep the resolution at 512 by 512 pixels, and use single-step models like SDXL Turbo that form images with a fraction of the usual math. Utilizing AVX2 instructions and single-step models allows a standard laptop processor to handle complex generation tasks that would normally require a much newer machine. The result is a 2017 laptop successfully running text-to-speech and coding workflows. It's a demonstration that local AI isn't just for the latest hardware. There is a growing realization in the industry that massive, uncompressed models aren't always necessary for high-level daily tasks. Developers are now training small language models on highly curated data, specifically intended to run efficiently on standard desktop processors. Practical tools for writing, coding, and basic image generation are no longer locked behind the latest hardware. With the right optimization, these capabilities are accessible on the machines many people already own.